Hello everyone, welcome to the next lecture of the course. In this lecture, we shall see how to do analysis for a turbo component with a profile boundary condition. So far we have given a constant value boundary condition. Now we shall see how to give a variable profile condition. For example, we shall take rotor 37 in this example and then we shall apply a profile boundary condition as shown here. With respect to radius, that is from hub to tip, the total pressure condition is varying as shown here. In this case, let us see how to specify this kind of profile boundary condition in the CFX preprocessor. We shall take an example like this, where with respect to the blade height, that is from 0 to 100% span, the total pressure is varying. Here the profile boundary condition is given for the rotor 37. The hub radius and shroud radius are specified here at the inlet. The total pressure and total temperature are specified here. We can see with varying span location, the total pressure is varying here. Similarly, the swirl angle is varying here. So, we have calculated the variation of total pressure with respect to the radius values. We have converted the span location into radius values. 0 refers to the hub radius, that is 0.175259, and span 1 refers to the shroud radius, 0.256631. So, with respect to the variation in radius, the total pressure varies and the swirl angle varies. The swirl angle is specified in terms of velocity components, that is axial component as well as tangential component. The radial velocity is 0 here. So we shall see how to specify the variation of total pressure and the velocity components with respect to radius in CFX preprocessor. There are two methods to input this profile condition. The first method is giving the user function, where we shall separately enter the values of radius and total pressure, and similarly for radius and velocity components. That is called user functions. The other method is using the profile data, which is Ansys CFX template, where we can input all the variation in a specified format, which can be used for specifying the profile condition inside CFX preprocessor. We shall see the methods one by one. In user functions, we shall specify radius versus total pressure or velocity component, and we can import this user function into CFX preprocessor. It will be entered like this. Here we have to specify the argument units, that is the radius value units, and the result units, that is the total pressure units here. We can extend the range from minimum to maximum if it is not meeting the hub and shroud limits. This is for user functions. The second method is called profile data. Here we have to enter the data in a single CSV file in the specified format. We have to specify the name of the file, the spatial fields which we have taken. For example, in this case we have taken the radius value. Usually for three-dimensional case, people will be specifying three spatial fields, that is x, y, z. But for this case, we are specifying the variation of pressure and velocity components in only one direction, that is along the radius. So we can use only one spatial field for this case. And in the last section, you have to specify the data, that is radius, total pressure, velocity axial component, velocity tangential component variation. We have to import the single CSV file in CFX preprocessor as shown here. So we have to specify the units and other inputs in the CSV file. The preprocessor will automatically take the units and other details directly from the input file. Now let us see both the methods one by one and check the results. Let us open CFX preprocessor. Now CFX preprocessor is open. We have imported the rotor 37 CFX file. In this case, the R1 inlet is given as a constant value, total pressure, total temperature, and flow direction. There is no variation with respect to the radius or spatial field. Now let us see the variation of total pressure and velocity components in this Excel sheet. Here we can see with respect to span, the total pressure and swirl angle are varying. We shall also see how the axial velocity and tangential velocity components vary with respect to radius. Now we shall import this profile condition into CFX preprocessor. In the first method, we have to import the radius versus pressure separately and the radius versus other velocity component separately. We have to use user function for that purpose. Let us open preprocessor. Here we have to use user functions. We can right click user function and then insert user function. Click user function. We can name it as total pressure. Click OK. We have to specify the argument units, that is x versus y. Here the x value is radius and the unit is meter, and the result unit is kilopascal for total pressure. Here we can enter the data for each and every radius and total pressure. or we can directly import the data. We shall save this data, that is radius and total pressure, into a separate CSV file or text file and import them. We shall save it as a CSV file. Click save. We can create a new file. We can copy the radius and axial velocity component, paste the values, save as axial velocity component. Similarly, we can save radius versus tangential velocity component. Now we shall go back to preprocessor. First we shall import the values of total pressure. Right click in this window and then choose import data. Go to the concern folder and then choose total pressure inlet.csv. Click open. Now it has imported both the values, that is radius versus total pressure. We can extend the range from maximum to minimum if it is not touching the hub and shroud limits. Click OK. Now the user function is imported. We shall use this user function to specify the boundary condition. Go to R1 inlet, go to boundary details. Here in this relative pressure, click this expressions. You can right click here and then go to functions, user function, total pressure. So here we have to specify the total pressure as a function of radius. So first we have to specify the expression for radius. We shall go to expressions, right click, insert, expression, radius. I am entering the value RAD. The radius is given by square root of x square plus y square. Z is the axial direction and then x and y are the other two directions. So radius is given by square root of x square plus y square. Click apply. We shall come back to R1 inlet boundary. So we have to specify the function total pressure as a function of radius. Now click apply. There is an error here. I think the expression is not given properly. Here we have to give x power 2. Click apply. Now we can see the profile boundary condition is given properly. Total pressure of radius. We can plot this total pressure using the plot options. We can choose boundary contour and then choose the relative pressure. Click apply. We can see the variation of total pressure as a contour plot. To see without the mesh grid lines, we can choose this boundary contour. Here you can see the total pressure at the center region is more than the hub and shroud region. Now in the next step, we shall import the user functions for axial velocity component as well as tangential velocity component. Right click user function and then insert both the functions. Velocity axial, the argument unit is meter, the result unit is nil. There is no unit for the component values. We can right click here and the import data, velocity axial. We can extend the range, click OK. Similarly, we can import the velocity component in tangential direction. The argument unit is meter, the result unit is nil. We can import the data, extend minimum and maximum, click OK. We shall go back to R1 inlet. In the boundary details, in the flow direction, choose cylindrical components. The axial component will be given by the expression. Right click, functions, user, velocity axial of radius. The radial component will be 0. The theta component will be, click this button for expressions, right click, functions, user, velocity tangential. And it is a function of radius, so we have to enter RAD in the brackets. Click apply. Here we can see the plot options as a boundary vector for velocity components. We can uncheck this and then see the cylindrical components. Click apply. This is the velocity vector in the inlet of the rotor. Now the case is ready. We can save the case file and save the definition file for solving the case. This is the first method. Now we shall see the second method.